Okay, good morning. Let's start our today's lecture. And the theme of our lecture, tangent to conics. What does mean tangent line? First of all, I define the tangent line. We have the so-called smooth curve. Let L be a smooth curve. And let's consider 2 points on this curve, P and Q. Exists unique straight line which passes through these 2 points. This straight line is called secant. And let's second point Q goes to P, and in the limiting position, secant coincides with straight line which has only one common point with curve, and this second line is called tangent straight line. We suggest that this curve is smooth. The curve can be defined to parametric equation if we have reference system in the plane, and we can consider 2 functions which depends from parameter t x and y t, and we suggest that both functions are smooth. It means that we can consider a derivative from this function. The rule infinitely many derivatives. From a school course is well known that if our curve is a graph of the function f at from x, in this case the tangent is defined by the following equation: y minus y0 is equal derivative f prime in the point x0 times x minus x0. If P is some distinguished point, and we consider the tangent which through this point P. But in our case, we consider the we independently obtain the formula for tangent curve. The coefficient in the equation of tangent line is called slope of the tangent line, and this number is also called the slope of the curve in this point. The slope of the curve in this point. By definition, the slope of the curve is the slope of the tangent line in this point. And let's start. And first of all, we obtain the exact formula for the tangent line for parabola. I recall that standard equation for parabola is y square is equal to px. And theorem 1. The slope, item 1, the slope of the parabola is defined by its standard equation. At any point is equal to parameter p divided by the ordinate of this point. Let me point P with coordinates x1, y1, and in this case we obtain that slope is equal the ratio P y1 slope. Item 2. The tangent to the parabola at point P with coordinates x1, y1 has the equation has the following equation: y1y is equal p times x plus x1. x1, y1 be the coordinates of the point P. In this point, we consider the tangent line to our parabola, and x and y are the variables. Let's consider the standard equation of the parabola. I recall that in this case we consider some distinguished reference system, and in this reference coordinate system the parabola has the following equation: y square is equal to px, and in this case the point F, which has coordinates P, the ratio P to 0, is called focus, and the straight line is defined the equation x is equal minus ratio minus P divided 2 is called directrix, and by geometrical way the parabola is defined by the condition: the distance from any point of the parabola to focus is equal to the distance to the directrix by definition. And we was reduced from this geometrical condition, the standard equation of parabola, which is equal y square is equal to times p times x. And let p be the point on the parabola, and this point has the coordinates x1, y1. And let's consider other point q, and let the coordinates of this point is x1 plus h, y1 plus k. And let's consider the second PQ. Second straight line. And we suggest that point Q goes to point P, and when the point Q goes to point P, the second change its position and tends to the position of the tangent straight line. And tangent straight line is a limiting position of the second PQ when Q tends to P. And in this case, easy to see, by definition, the slope of the curve and the slope of the tangent straight line in point P, by definition, is equal the ratio y plus p minus y divided x plus x1 plus h minus x1. And in this case, we obtain the following expression for the slope. The slope is equal limit the ratio k to h. And let's calculate. Excuse me. And in this case, we obtain that the equation for the tangent line is equal y minus y1 is equal m times x minus x1. And let's calculate this ratio k to h. Easy to see because the point x1 and y1 lies on the parabola. These points, the coordinates of these points are satisfied to the parabola equation. And easy to see, we have two equations for which related the coordinate x1 and y1. Y1 square is equal to p x1. And also point Q also lies on our parabola, and its coordinates also satisfy the equation of parabola. And we obtain other equation, y plus k square is equal to p x plus x1. Oh, I'm sorry, x1 plus h, x1 plus h. We have the following system, and let's consider the difference between this equation. Let's subtract them from first equation, from second equation, first equation. Easy to see that the second equation can be written in the following form: y1 square plus 2y1k plus k square is equal to p x1 plus h. And we can rewrite in the following form. Sorry. Let me rewrite this equation on the next blackboard. And the first equation is equal y1 square is equal to p x1, and the second equation is equal y1 square plus k times 2y plus k is equal to p x1 plus 2ph. And after subtracting from second equation first equation, we obtain the following equality: k times 2y plus k is equal to ph. Easy to see that the difference that the difference k to h from this equation, easy to see. From this equation, we obtain the difference k to p is equal the ratio to h oh, I'm sorry. KH, I'm sorry, KH. kh to p times to k to kh to y1 plus k. And in the limit, when h tends to 0, k tends to 0, we obtain that this ratio is equal p divided y1, and we obtain the exact value for the slope of our tangent line. And after then we can substitute the expression for the m in our equation of straight line which pass from the point with coordinates x1 and y1 and has a slope m, and the slope is equal the ratio py1. And after them we can rewrite our equation in this form. Easy to see that this equation is equal y1 minus y1 square is equal px minus px1. And we can see that y1 square is equal to px1, and final form of our equation is the following: y1 is equal px minus px1 plus y1 square, which is equal to px1 and is equal px plus px1. And we obtain the final form of our equation. y1y is equal p times the sum x plus x1. And first item of our theorem is proved, and second item is also proved. Any question? The formula for the slope. This formula for the slope of tangent straight line. We obtain this. Formula. When k tends to 0, this formula transforms this formula. The slope or the coefficients k for the coefficients in the M is equal to the ratio P y1. Okay. The first assertion of our lecture, and let's consider some simple example of application of this formula. Example. Let we have the following equation: y square 12x, and the equation to find the equation of tangent straight line to this parabola in the point with coordinates 1 divided 3 minus 2. Let's check that this point lies on our parabola. Y square minus 2 square is equal 4, is equal 12 times 1 divided 3, and 4 is equal 4. And this point actually lies on our parabola. And we can consider the equation of the parabola in our case P is equal 6, y1 is equal minus 2, and we obtain minus 2y1 is equal 6 times x plus 1 divided 3, and we obtain 6x plus 2. Or y1 is equal minus, I'm sorry, y, not y1. Y is equal minus 3x minus 1. Y plus 3x plus 1 is equal to 0. The final form of our tangent line. Let's continue. And first part of tangent straight line of parabola is some properties of tangent line to parabola. And let me formulate some properties. Yes. Any question?
Sorry. Yes. Y is P equal to 6. Oh, sorry.
The canonical equation of parabola is equal y square is equal to px, and in our case 2p is equal 12 in our case, and then p is equal 12 divided 2, and we obtain that p is equal
Thank you.
6.
Yes.
Okay.
Sorry.
Okay. Let's consider the draw. Parabola. And let P some arbitrary point of parabola which has the coordinates x1, y1, f be the focus which has the coordinate p divided to 0, and we have also directrix which has the equation x is equal p divided 2, and let me let Q be the point which is projection of point P on the x o x, and we have also tangent straight line, and let's consider the normal line. Normal line is perpendicular to tangent in the point P. Easy to see if equation of tangent is equal y minus y1 is equal the ratio p y1 times x minus x1 tangent line. In this case, the normal has the coefficient, angle coefficient, which is m normal is equal to the ratio minus 1 m tangent, and the equation of the normal line is equal to the ratio y1 to p x minus x1. I recall that the geometrical sense of this coefficient is the tangent of the slope of the tangent straight line, and as the normal is a straight line which perpendicular to our tangent straight line, we have the following relation between these coefficients. The product of the tangent of two perpendicular straight line is equal exactly -1. We change sine and cosine and change one of the signs. And in this case, we obtain, if we consider the ratio sine cosine phi, and we shifted, we change sine and cosine and shifted. I'm sorry. If we change the angle P2 we obtain minus cosine phi divided sine phi, and the product of this expression and this expression is equal exactly -1. And using this simple observation, we obtain that the formula for the normal straight line is equal exactly the same form as the formula for the equation of the tangent straight line, but we change the coefficients, the slope in the tangent on the inverse expression with opposite sign, And let's introduce the new notion. Let's consider the point intersection of the normal straight line and x and axis OX. And let Q be the point intersection of normal straight line, and let and N and be the point of intersection of tangent straight line with x OX. And property 1.
Question.
Okay. Any question?
Sorry, I have a question. Yes. Two questions. One is why minus y1 is equal to p over y1, and y minus y1 is equal to minus y1 over p.
Why? The question why? Okay, I repeat my explanation. We have the angle between tangent straight line and axis OX. This angle is alpha, and we rotate our tangent straight line, rotate on the straight angle, and
thank you.
We obtain the so-called normal straight line. And easy to see that the angle between normal straight line and axis OX is equal alpha plus p divided 2. We added to the alpha the angle p divided 2 and obtain the angle between XOX and
yes, I understand. And
yes.
One more question: is
yes.
it possible to
do you understand? Because this coefficient is equal minus y divided p or not?
Yes.
Yes. Okay. Yes.
And one more question is: can we also choose the point P like 0 and 0? I mean, the tangent line starting from the beginning of the parabola.
Repeat, please.
Choosing the point P,
in the yes.
beginning of the parabola. I mean, in the most left-hand side of the parabola. External.
P is arbitrary point. P is the arbitrary point on our parabola. We fixed this point and consider the straight line which pass from this point. We have any point.
Where will be
we fixed
the point N then?
Okay. Yes. And we fixed such point P on our parabola and consider the tangent straight line. And this straight line, tangent straight line, intersect axis OX in the point N, the point of intersection. Straight line, tangent straight line, and axis OX, point N. And the same way, we consider the intersection, the point intersection of normal straight line and the axis OX. We obtain 2 points. If we fixed P, we also fixed N and Q. If we change P, both of these points are changed.
Thank you.
But I fixed point P and consider also 2 points N, the point intersection of tangent straight line and axis OX, and other point Q,
Excuse me.
Yes. If I change. Yes.
If we choose a point P at the coordinate at the origin of our hyperbola, then the points N will be also at the origin.
Excuse me. We also now we consider only a parabola in our. We consider in the first part we consider only parabola at tangent line to parabola. Hyperbola
yes.
and ellipse we consider later. Okay. Only parabola.
I said a parabola.
Yes, this parabola.
Thank you very much.
I'm going to formulate the some property of parabola which related with 2 points. The property is the following. The point O divided the segment NQ on 2 equal parts. I reproduce more exactly. Property 1. Property 1. This segment NQ divided by point O onto 2 equal parts, namely TQ is bisected at the origin. And O is equal OQ. Let's prove this property. Let's prove this property. We calculate the distance between O and Q. This distance is exactly equal to the first coordinate of the point Q. Easy to calculate this coordinates. In this equation, we can consider that the value of variable y is equal 0 and calculate the value of variable x. And this value is exactly a coordinate of the point Q. We obtain minus y1 is equal minus y1 px plus maybe easy to see, we obtain minus y p is equal y1 times x minus x1. Yes?
You wrote NQ is equal to QQ.
Yes. We calculate the first coordinate
TQ
of point Q.
At...
Yes, the point Q lies on the normal straight line, and all points of the straight line are satisfied this equation, the equation of the straight line. The intersection point has the second coordinate y, the second coordinate y of point Q is equal 0. And in this equation, I put the value of these coordinates 0.
I'm sorry, Professor. The property 1 says NO equals. Yeah.
The question about this equality.
Yes, yes, yeah.
I try to prove that this distance, this distance is equal to this.
Okay, thank you.
And I try to calculate Q, the coordinate Q. And easy to see that minus P is equal x minus x1, and we obtain x is equal x1 minus P. I'm sorry, minus. I'm mistake. Minus plus and x is equal P plus x1. Minus P1 P plus x1, maybe. Okay. This distance is equal P plus x1 My draw is not agree with calculation. Okay, let's calculate the point intersection of the tangent and axis OX, and we put the value of coordinate y 0 in the second equation, and we obtain the following expression: minus y1 square is equal px minus x1, and we obtain px1 minus y1 square is equal px, and y1 is equal minus 2p y1 square is equal to 2p x1, and we obtain minus px1 is equal to x. X is equal minus x1. Ah, okay. It's mistake. Is mistake. And f for chi. I'm sorry. For chi is divided. Sorry. I'm sorry, так. I'm sorry. I correct this mistake. Let's introduce n be point of intersection tangent, straight line, q okay. Let's excuse me. I correct. Let t be the point of intersection of tangent straight line, n be the point of intersection of normal straight line, and q be the projection of point P. And one. And let's introduce two notion. Let's introduce the notion. This straight line let's take Q, we shall call it subtangent. This projection, TQ is the projection of the segment of straight line between point of P and T on the axis of X, this projection, we shall call subtangent, and Qn we shall call subnormal. And property 1. The subtangent this the Q is bisected by point O. And let's repeat our calculation. The point T has the coordinate x. From this equation we obtain minus y1 is equal p divided y1 x minus x1, and we obtain minus y1 square is equal px minus px1, and we obtain pxy minus y1 square is equal px. Px1 minus 2px1 is equal px, and we obtain that x is equal minus x1 minus px1 equal px, and x is equal x1. The coordinate t is equal minus x1, and coordinate q is equal x1, and we obtain the first property. And the second property, which was proved before, is asserts that Tn is divided by focus onto equal part, property 2. Property 2. Tf is equal Fn. We proved this property, and from this equation we obtain that minus y1 times p is equal minus y1 times x minus x1, and we obtain minus p is equal x minus x1, and we obtain x is equal x1 minus p. This point has a coordinate x1 minus p. Oh yeah, I'm sorry. Minus mistake maybe. Minus x is equal and for chi has normal p I'm sorry minus p plus this mistake x1 plus p. My mistake is subtraction, and we obtain that the coordinate of point n x1 plus p and the coordinate minus x1, and easy to see that the distance TF is equal x1 plus we obtain that the coordinate point T, the first coordinate, is equal minus x1. The coordinate f is equal p1, 0, and the coordinate of point n is equal x1 plus p0. And this distance, x1 plus p minus p divided 2, equal x plus p minus p divided 2, and equal x plus p divided 2. And this distance, TF is equal x1 plus p2, and the distance fn is equal difference between values of first coordinate x1 plus p minus p divided 2, and equal x plus p divided 2. And we obtain that these two distances are equal. Any questions?
Yes. In property 1, we proved x equals minus x1, and then in property 2, we proved x equals x1 plus p. I think there's a mistake.
Yes. Property 1. We assert that the origin divided we have two segments, T Q, Q, B projection P. And this property asserts that origin divided this segment on two equal parts. And property 2 asserts that the segment Tn, T is intersection point of tangent straight line, and or axis OX, and N be the same intersection point by the normal straight line. And this segment divided onto equal part by focus. And we assert this distance between T, F, and distance between F and N. We know that the first all 3 points lies on the axis OX, and the distance of the segment is exactly equal the difference between its first coordinates. And we calculate the first coordinates of this point. By definition, focus has the first coordinate p divided 2. And we calculate the first coordinate of point N, which the intersection point of normal straight line and axis OX. And this first coordinate is equal x1 plus p. Our calculation is the following. From this equation, in this equation we put the value y is equal 0, and I divide it by minus y1, and obtain p is equal x minus x1, and x is equal x1 plus p. Do you understand this calculation?
Yes.
And, yes, and this point of intersection, normal straight line. The same way we obtain that the intersection of the tangent straight line and axis or x from the first equation is equal minus x1. This coordinate is equal minus x1. After them, easy to calculate this difference. P1 minus x1 is equal p divided 2 plus x1. And this distance, the same way, can be calculated. X1 plus p minus p divided 2. And we obtain x plus p divided 2. And we obtain that these distances are equal. Do you understand? Yes?
Yes, thank you.
Okay. And the main property 3. This property is the following. We obtain the equality of two angles. The equality to angle. can compare to angle. Let R be the point intersection of the straight line which pass from P and parallel to the axis OX. PR is perpendicular to the directrix. And let's compare the two angles. Let's minus P divided 2 foci point P PR PF T TPF I'm going to consider the following two angles, these angles and these angles. I assert that these two angles are coincide. Property 2. Oh, property 3, sorry. The tangent divided, the tangent bisect the angle RPF. Angle RPT is equal angle TPF. The so-called Fourier property of the parabola. Maybe 2 minutes, and I try to finish this proof. Easy to see that this perpendicular to the normal, and we have this segment is equal this RP is equal PF. I don't understand that. This. Okay, this. Okay, let's prove this angle is equal this. Easy to see that RP is equal PF by definition of parabola. This is equal this. And this distance between T and F is equal the distance RP. As was proved above. because the coordinate this the coordinate t is equal x. The coordinate t is equal to t x1 plus p, and this coordinate is equal t plus x1 plus p divided 2, and this coordinate is equal p divided 2 x1 plus p. This distance is equal also x plus p divided 2. Oh, I'm sorry. The coordinate t is equal minus x1, 0, and tf is equal x1 plus p2, and this distance is equal x plus p divided 2, and this segment RP is equal PF, and we obtain that TR PF be rhombus. And in the rhombus, this segment is diagonal. And diagonal divided the angle in the rhombus onto equal part. And we obtain this angle is equal to this. And we obtain the natural sequences of this property. If we have in the search of some light maybe in this point, and the rays when can be reflected in the any point, and after reflection the trace of the ray, the straight line which parallel to x o x, and if we have rays which moved parallel to the straight line in any point of parabola after reflection, which goes to the point f, and any straight line we have the straight line which moved parallel one other and parallel to the x o x. All these rays after reflection moved to the focus. Excuse me, I'm finished this point, this part. Any question maybe?
No, thank you.
Thank you.